Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas. Hey everyone, and welcome back to the Building Science Podcast. My name is Michael.
And I'm Christoph Irwin. Hello.
And we're back with you for our fourth episode of our 5-part series on the control layers. We started out with a pretty basic introduction, and we've worked through one control layer per episode following. And we're working with the vapor control layer on this episode. So we've got rain, you've got air, you've got vapor, and you've got thermal control layers. And we're going to dive into as much depth as we possibly can about the vapor control layer this week. So with that, Christoph, take it away.
All right. Thank you, Michael. So actually, I'm going to contradict that a slight bit. I think that there's artificial depth in the vapor control layer discussion in our industry, and it's centers around this concept of perm ratings, and we're going to be talking about that. But being me, I want to start hierarchically and remind us of some of the principles that we've covered. When we're talking about vapor control, we're talking about moisture control. So vapor, just to get some definitions out of the way, water vapor is what we mean when we say vapor. We're not referring to some other item. We're referring to an implicit constituent ingredient of air, which is water vapor. And the reason it's called water vapor and not water gas, so we don't say we have nitrogen vapor in the air, but we do have water vapor in the air. And the reason we call it vapor is because it is near the transition point between solid, liquid, and vapor. Let me clarify that. It's called vapor in the air because it's near the transition point between liquid and vapor. One interesting feature of living on Earth is that water is one of, if not the only, naturally occurring element that naturally occurs in our world in all three phases. So that was a long way of saying that when we talk about vapor, we're talking about moisture. And so when we're talking about moisture, the same principles apply. Many of the same principles that we applied to what we call bulk water or liquid water apply to vapor control. Specifically, the downhill concept is still applicable. Liquid water moves downhill, water vapor moves downhill, but the hill is defined as vapor pressure, high vapor pressure to low vapor pressure. Moisture looks for an opening, a crack, or a gap. So does water vapor. It just so happens that water vapor is exceedingly small. We already mentioned recently about how small an air molecule is. Water molecules are even smaller. So they can move right through. I think, we talked on this previous podcast about your newspaper getting wet, going right through the plastic. So that's water vapor moving through there. It follows the path of least resistance, and that means that if the vapor can get transported by the air into or through your assembly, it's going to do that. It's not going to work its way right through the materials. It always goes from high to low. We talked about that. It's going to go from a place of high to low vapor pressure. When it comes to moisture, there's these 4 classic hierarchical ways that moisture moves through your building. So I want to make sure we're aware of these. The number one way that moisture can move into or through a building assembly, possibly creating issues, is piggybacking along with the air. The number 2 way is capillary action. And, the basic gist there is that surface tension and the motion of moisture through trees and wood still happens even when we cut the tree down. Obviously, water can flow in bulk form, but there's chances are you're working really hard to control that. And then the 4th way is vapor diffusion. So that's kind of hierarchical as well. Air, capillarity, liquid flow, and then vapor diffusion. All right, so now I think we can talk a little bit more in depth about vapor movement through your assemblies or into your assemblies. And it's unfortunate, but it is impossible to really talk about vapor control. Well, maybe not impossible, but to talk about vapor control in a meaningful way, we need to introduce the term Perm Rating. So by Perm Rating, it's actually perm or permeance. And then permeability is the permeance that varies with thickness. So typically what a perm rating is we've defined the material and we've defined the thickness of the material. When we've done that, we can then say that we now can call it a perm rating. We can say how many perms are associated with that. So permeance is a material property. Permeability varies with thickness. But don't try to remember that. It's not that important. What's important is to realize that this is not just some fictional property, that it is a property of the material. And here's how it's defined. This is something that I haven't heard really said that much, but it really helped me to feel grounded with the idea of a perm. So imagine 1 square foot of material. Let's say a piece of sheetrock as big as a standard piece of notebook paper, right? That's roughly a square foot. So you have that piece of sheetrock, and then you're going to see how much moisture in vapor form moves directly through that piece of sheetrock, and you want to characterize that with some number. So what do? Well, you go to ASTM and you find the standardized test protocol and you follow it. That would say you take a square foot of the material and you put a pressure difference across it, right? We need a driving force. So you put a pressure difference across it of 1 inch of mercury, and then you wait a certain period of time, and in this case it's an hour, and then you count how many grains of moisture, we'll touch on that in a minute, how many grains of moisture have moved through the material from one side to the other. And so let's say it's sheetrock and you count up that you've got 50 grains of moisture have moved across your 1 square foot of material in 1 hour when it was subjected to a pressure difference of 1 inch of mercury. Well, that 50 grains that occurred is going to define the permeance of that material, the perm rating of that material, as 50 perms. So what I want you to keep in mind there is that something actually happened, something physical happened to the material, grains of moisture moved through it, and the number of grains that moved through it under those conditions that we prescribed define the perm rating. What does that mean is not a simple answer. And I can tell you one thing that it definitely seems to have meant over the last few years, if not decades in our industry, is a lot of foment and controversy about what's the proper perm rating that was unwarranted. Before we go there, let's make sure we talk about grains. So a grain comes from, as far as I know, it's a historical term, and it actually comes from grain, like grains of wheat or other grains. And it's basically a measure of a small piece of water. And as far as I know, also, it's not a physical thing. It can be defined as physical by saying that there's 7,003, typically referred to as 7,000 grains of moisture in a pound of water. If you have a pint bottle of water or a pint bottle of something approximating water, like beer, you can imagine staring at that and saying, I'm going to divide you into 7,000 pieces.
That's an unfortunate beer.
It's a very small beer. So if you have that 1/7,000th of a pint beer, how big is it? Well, it just so happens if you take the volume and do some math, if I didn't do it wrong, that would be a very small, and I'm going to use a very small sphere of beer, and it would be about as big as the letter O on a penny where it says 1 cent. So that's pretty big, really. It's huge. It's vastly bigger than the size of a water molecule. So a perm is not a molecular measure of water quantity. It is inherited quality. Oh, excuse me, I said perm. A grain. It is a physical measure of water, but it's not a molecular measure of water. So when we're measuring grains, it is a fantastic unit of measure. I mean, this is more into psychrometrics or HVAC, but grains are where I recommend everyone listening take themselves in their understanding when they want to think about moisture, even in the indoor air. Because on a dry winter day, you have single digits of grains in a pound of air outside. In a hot, humid climate in the attic in summer, you can have a couple hundred grains in a pound of air. Indoor, inside your space, you'll have 50 to 60, let's say, 55 to 65 grains in a pound of air. So grains become a very precise way to discuss moisture, quantities of moisture in various spaces. And that's why they're used for perms. It makes for some convenient numbers. So let's talk about perm rating classifications, speaking of convenient numbers. Let's think in powers of 10. You start with the number 1. If you go 10 less than that, you're at 0.1. 10 more than that, you're at 10. So if you can just remember that, 0.1, 1, and 10, there you've got your framework to understand perms. The first way we talk about perm ratings for materials, keep in mind, when you're talking about a perm rating, you have defined what material and you have defined what thickness. But that's not a problem for us, right? It's usually pretty convenient. You know what material and you know how thick you're going to be wanting that material to be for your application. So we're looking at 0.1. Less than 0.1 perms is considered a vapor barrier. Now, technically, it's not a vapor barrier because it's not 0. It's just less than 0.1. So it's called a class 1 vapor diffusion retarder. I bring up that term vapor barrier. Won't go off on the tangent. You see the word vapor barrier used interchangeably with weather resistive barrier, control layers, air diffusion retarder, all these different terms that are out there. But a vapor barrier is not the same as a weather resistive barrier. That was an old school use of the term vapor barrier. It's actually a class 1 vapor diffusion retarder, and it is considered to be vapor impermeable. Right? It's not quite, but it's relatively vapor impermeable, so we're going to call it vapor impermeable, less than 0.1 perms. Now we're at the next step up. We're going to go from 0.1 to 1 perms. So that's a class 2 vapor retarder, and it is vapor semi-impermeable. A good example for that, on the order of that, would be like OSB or plywood. Now, it's not technically less than 1, but it's around there. Maybe it would be better to say, in fact, I'm going to switch. I'm going to say XPS or something like that, extruded polystyrene. I'm going to say that is a good example of class 2, depending on the coating, but if it's not coated with foil, it's around 0.8, something like that. So that's an example of vapor semi-impermeable. Vapor is definitely having some trouble moving through that material. You're only getting from 0.1 to 1 grain in an hour in a square foot with an inch of mercury, but some diffusion occurs. Then you get into the material category where it is between 1 and 10. Keep in mind our dividing lines are less than 0.1, between 0.1 and 1, between 1 and 10. We're looking at a class 3 vapor diffusion retarder if we're between 1 and 10. And it is defined as vapor semi-permeable, not vapor semi-impermeable. But now we're saying, a meaningful number of grains are making it through this. And the word meaningful was in italics or quotes when I just said that. And we'll get to that next. So the last one is anything where mu, the perm rating, is greater than 10. And that's called vapor permeable. For instance, Tyvek is a mu of around 60. It really just depends on which company's product you're looking at there. But WRBs are basically happy to be vapor open, but liquid water closed. That's their goal. So touching in on that comment about meaningful, right? So we're talking about perms being a meaningful metric for building assemblies. And therein lies a large conversation, a large sprawling heap of ideas that it would be impossible for me to help sort out for you fully, but I'll just say this. When you're talking about perm ratings, it's very important to be talking about it in the context of a designed wall assembly or a designed roof assembly, and it is not all about the perm ratings in that context. We're going to be definitely paying attention to air transport through that assembly because that is a couple orders of magnitude more important than perm ratings of that material. It unfortunately, or fortunately, it doesn't matter. A bunch of controversy is good because it makes interest in this field. But there's a lot of thinking out there that is as though, just tell me what perm rating I need. And I need to know the perm rating of every material in my assembly. When that's happening without cognizance of the overall performance of the assembly, it's like focusing myopically on something. It's like winding your watch on the way to the gallows. It doesn't make sense. So what you really need to do is when we're focusing on anything about our assembly, we need to think, okay, what's our organizing principle here? What is our goal to be thinking about this at all? And the goal is probably durability, right? We're worried about moisture. We're worried about it getting in. We're worried about organic materials, moisture and mold. And that's durability. And that's a great thing to be concerned about. But to assume that perm rating is a proxy for durability, that is unrealistic. That's too big of a leap. You just went too far. What is a proxy for durability is the ability for a material to dry out. and the ability for a material to not get wet. They're related. What we assume, and we're not pessimists as building science consultants here, we're not pessimistic. It is very important to realize that no matter how much effort we go to, within reason, that moisture is going to be able to get in. It could be indoor generated moisture that gets into our assembly. It could be a flat out leak. It could be wind driven rain.
And there's a lot of indoor moisture that occurs every single day, whether from cooking, from people breathing at night.
Plants,
so
dogs.
Certainly possible, yeah.
Yeah, so it's a reasonable assumption to say that your building assemblies are going to be assailed by moisture and you need to provide for their drying. And durability doesn't mean things don't get wet. Durability means that as things get wet, they dry faster, right? The fancy way you hear that said is that the rate of wetting is exceeded by the rate of drying. And by the way, those rates don't have to be, minute by minute. I got this wet this minute, I'm going to dry out this minute. It can be seasonal. You can have a building assembly that accumulates moisture for a season and is, going down. It's getting pretty unhappy and pretty soggy. And as long as the next season comes along and fully dries it, that building assembly can last quite a while. It's better if that doesn't happen. It's better that if the rate of wetting never gets to levels where things are really unhappy. But my point is that I said it already, but I'm going to say it again. To say that a perm rating of a material is a good proxy for durability is not the case. But that's sort of the role it's been cast. It's like everybody's saying, what's the perm rating of this and the perm rating of that? And what they mean is, how can I evaluate whether my assembly is going to be durable or not? Which is a great thing to be thinking about, but then to swallow it into perms is not. If you want to evaluate how your material is whether it's going to be durable or not, there's, I guess, a fork in the road. You can go one of two ways. You can use established assemblies where the characteristics are known and there's been testing done and it's shown to work. Or maybe the testing is real world. It's evolved over time and this assembly works. That's a little dangerous given that there's other changes to the building enclosures with air tightness and thermal control. But the other way is hygrothermal modeling. And, even better than that, the implicit empirical measurements that undergird hygrothermal modeling right now. So, meaning that you put things into a certain, under a certain moisture stress and then put it under there for a certain period of time and take it out and sample it and see how much moisture was in it. Why are we doing that? Why are we going to all that trouble to sample these things, right? And keep in mind it goes back to durability. And it goes back to durability because we want it to last. I just went off on a thread that I can't follow. So if we want something to last, what we mean is we don't want it to be eaten by little organisms. We don't want it to rot or mold, right? So we build mostly out of organic materials right now. We use a lot of them in our building assemblies and inside our buildings. So we want to make sure that those things last and those materials accumulate moisture. And this is another big subject, right? So this is where you want to Google Lou Harriman, Moisture Control Handbook. You want to read Bill Wood's book, Moisture in Buildings or Water in Buildings. These are fantastic references to dig deeper. But what we're saying is when we're talking about moisture in our building materials is we don't want the surfaces of the moisture to get at a surface relative humidity above 0.8 because at that level, these organic materials will start to grow and start to eat your building materials. There's so much more to say about this. I'm feeling like a horse where the reins are really pulled in because we're not here to talk about mold today per se. Well, we're here today, and we could talk about that in the future. It's a good one. What we want to talk about today is why we don't want moisture in our materials, and it's because they won't last a long time. And even more subtle than that is if you're accumulating moisture in your materials, lots of indoor air quality concerns or lots of indoor air quality problems scale with elevated moisture. So dust mites being a good example of that. Dust mite feces are something we're really allergic to. Dust mites eat skin tissue. That means their digestive enzymes can dissolve our tissues. That means when those digestive enzymes, which are, it's kind of gross now, are implicitly mixed into their poo. When their poo touches our tissue, it starts to irritate it really strongly. So it's a very high allergen potency, and it scales with humidity. So we want to make sure that our building materials aren't humid. That actually is not quite related to the perm ratings. So let's talk about some of the numbers, some of the Mews, some of the perm ratings. 6 mil poly, we talked about, it's 0.06. OSB is around 2. Plywood is maybe slightly higher. All these are taken with a grain of salt. You need to take them with a grain of salt. And which is different than a grain of water. I don't actually know what a grain of salt is.
Oh, that's very good. It's tasty.
How many grains of salt in a pound? Expanded polystyrene, 1 inch of that unfaced, is on the order, it actually straddles the line there between vapor semi-impermeable and vapor semi-permeable, depending on who made it, right, I guess, or how that goes. It's on the order of 0.5 to 1.5, something like that. XPS is typically, if it's unfaced, it's typically a little bit higher, more like 2 to 6 perms. If you put foil facing on it, it goes very low. Like aluminum foil, it's probably 0.000 something. I've seen it written as 0, and I just somehow can't quite believe that 0 grains of moisture will make it through, but maybe it's 0. I'm not the authority on that, but don't line your buildings in an area where you need them to be vapor open with aluminum foil. Would be a good thing to talk about, and we will talk about that next. Open cell spray foam, closed cell spray foam. This is an important one to talk about. So if you have 3.5 inches of open cell spray foam, which is pretty common, it's going to have a perm rating in the 10s. In fact, I probably should have framed this discussion like that. It's probably better to not worry about the number per se, but to say, is it less than 0.1? Is it around 1? Is it around 10? Is it 10s, right? So open cell is, it's more than 10. It's in the 10s range. And closed cell is less than 1. It's not less than 0.1, right? So it's less than 1. And that's 2 inches of it I was referring to there. Let's see. Felt. Number 30 felt, right? And there's a discussion there about what is number 30 felt these days. And there's an ASTM test, but it's not what's called, 30-pound felt is not what's called number 30 felt. Number 30 felt, if it were to be marketed by some VC firm in Silicon Valley, they would probably say it is a smart molecule that dynamically adjusts based on the moisture content of the material to promote drying when circumstances permit. Something like that, or circumstances warrant. And what that means is there's a different perm rating for 30-pound felt dry or 30-pound felt wet. And it goes from less than 10, let's say 1 to 5 range, to several 10s, like 50 to 60 to 70 range when it's wet. So dry, it's more vapor closed than it is when it's wet. And there are a lot of intelligent people that like 30-pound felt precisely for that reason. They like the fact that if you ended up with water behind your weather-resistive barrier, so between the weather-resistive barrier and the sheathing, that if that weather-resistive barrier were felt, it would open up and allow the bulk water, which would have to turn to vapor, to go through the felt. In fact, if it were liquid water, it would soak through the felt. It would move through the felt. So let's talk about that. I think this is probably toward one of the last big topics, and it's a pretty big one. I think if any of you have tuned in just to hear about vapor control layers and perms, it's because it's darn confusing right now. We are at something like an inflection point in the industry, specifically in humid climates, where historically vapor open. This means perm ratings definitely above 1, maybe even above 10, right? So vapor open building assemblies were what was recommended for humid climates. What we're entering into is a state of the industry where it's recognized that if you have your entire building assembly to be vapor open, in terms of vapor, there's an imprecision now of defining where the interior space is versus the exterior space. Maybe to make a metaphor that's a little easier to understand, if we use open cell spray foam as our air barrier, and let's say we have a 2x4 assembly. Well, open cell spray foam, I haven't kept track of the latest, but it's around 3.5 inches of open cell spray foam is needed to define an air barrier. So what you're saying is that you're not saying that the air barrier occurs at the weather resistive barrier if you're using open cell spray foam to create your air barrier. You're not saying the air barrier occurs at the sheathing. You're not even saying it occurs at the inside face of the sheathing. You're saying that somewhere between the inside face of the sheathing and the back of the sheetrock, somewhere in that 3.5 inches of open cell spray foam, by the time you get to 3.5 inches in, now you can call it inside space. So that's kind of bizarro, isn't it? So if you think about that, that means I could go 3 inches in past the sheathing and say, okay, now that's inside space, which means that everything I just went through, which is all my insulation, the back of my sheathing, back of my weather resistive barrier, the air gap, if there is one, which I hope, and all the siding, all of that is considered outside. Same thing with perm ratings. What that means is there are more and more people and more case studies and more situations on the ground where the strategy has been to use a vapor closed, which typically means less than 1, a vapor closed material. And what this does is, in my opinion, my professional opinion, this puts things properly. This is saying right here, this is where inside and outside are separated from air, water, liquid water, and water vapor. And then you can put the thermal on either side. The outside's actually preferred. But once you define that, what you need to do is you need to make sure that the material on both sides of that vapor closed plane can dry, right? So you need to say, okay, everything inside of my vapor closed plane can dry to the inside, everything on the outside of it can dry to the outside. And drying to the inside is usually not a big deal because we don't use any other vapor closed surfaces, with the caveat of things like mirrors or whiteboards or some formaldehyde, phenol-based cabinets, things like that. So if you live in a humid climate and you're hanging a big mirror on the wall, your drywall's open, the latex paint is open, right? Latex paint, by the way, is single digits. It's 3 to 5 range for perm ratings. You want to make sure that your mirrors are hanging off the wall and that your whiteboards are hanging off the wall and things like that by around 1/4 inch or more, so that there could be some drying potential and we don't trap the moisture there. On the outside, happily for me, we're centralizing as an industry toward the recommendation of ventilated rain screens. And ventilated is different than vented. And what it means is you define a water control layer. And a water control layer is not a thing, it's a collection of things. It's flashings and coatings, and they can be peel and sticks, they can be sheet goods, they can be fluid applied. But what you're doing is you're defining a way liquid water will run out, and then you're also defining a way that air can flow into and out of your assembly to provide for drying. Something like the perfect wall concept would have this layer where you have your weather resistant barrier, and it could be vapor closed, and then all the insulation would be outside it, and then you'd have your air gap, and then you'd have your siding. We've had a situation here in Austin where there was a project that had a vapor control layer. I think it was CCW 705, which is a Carlisle product, and it's vapor closed. It's a peel and stick. It was applied with its primer as needs to be done. And then there were several inches. I don't remember exactly how many inches. This is Matt Reisinger with Reisinger Homes. You can just Google Perfect Wall Reisinger Homes. You'll hear it. Fantastic house, fantastic videos on this project. And so there was some controversy about, well, look, I'm putting extruded polystyrene right outside of my vapor control layer, which is vapor closed. So at the vapor control layer, I have no drying function. So if water gets in there, it's going to sit there between my XPS and my 705, my control layer. But and that's true. It's also true two things. One is that there's nothing organic in that vicinity to eat and to rot and to create problems. And two is that over time, especially because on the other side of that XPS layer, we have provided a lot of good drying, and gravity will take the water down, capillarity and airflow and heat will get in there and move the water out. You've provided for drying, and you've defined inside versus outside. Well, I think I could definitely come up with more things to say, but I think that's long enough. That's good enough for now. I think you have a sense of things. I'm going to do a little bit of a wrap up, right? So I want you to take, if there's only one thing I want you to take from this podcast, it is, well, it's that you like it and you want to listen to the next one. It is that drying and durability are not regulated by perm ratings alone. That perm ratings are not a good proxy for durability. Now that seems contradictory given the well-publicized and very important research that has shown that, especially in humid climates, in cooling-dominated climates in the summer, well, obviously if it's cooling-dominated summer, but humid, cooled buildings have a thermal drive and a vapor drive from outside to in, and if you have a vapor-closed surface inside that building, like a hotel with vinyl wallpaper, or a big mirror in a home, something like that, that's going to cause moisture accumulation behind that vapor-closed layer and cause rot. So if you use a vapor-closed layer, you need to make sure that you're providing for drying on both sides of it, drying to the inside, drying to the outside, or at least drying to whichever side of it is open. The other thing to take away from this is that please don't get hung up on the perm ratings, to really think of them as one ingredient in a larger recipe that it's thinking about the overall performance of the assembly, and that's rain, air, vapor, thermal, and that's providing for drying. And air is a big one. Air is more important than perms. If you're paying attention to perms at the expense of air, not paying attention to air, that's a problem. That's not a good idea. We also talked toward the end here about ventilated rain screens, and I said it's not the same as vented. I want to make sure you understand that basically it's pretty simple. If you have an opening at the bottom of your rain screen so that liquid water can come out and there's air can get in there, then it's vented, and that's good. That's better than an unvented assembly. It's becoming more normal. I think there's a lot of people in the industry that are still slow to accept it, but pay attention, watch, look at your job sites. You're seeing furring strips, you're seeing ventilated rain screens happening all the time. Ventilated versus vented. Vented was at the bottom, open at the bottom. Ventilated means it's open at the top and the bottom. And there's a number of product manufacturers with products to accomplish this. There's ways to skin that cat on your own with screens and things like that. So that's that one. Let's see. What else did I was thinking about? Okay, two more quick thoughts. One is references to dig deeper. And I would absolutely recommend Bill Wood's book, Water and Buildings. Lou Harriman has some fantastic ASHRAE articles on this. I'm trying to remember a good source. They're available in article form, but ASHRAE's Guide to Humid Climates. It's a hardcover book. It's fantastic. It's going to cover all the topics I just touched on and more. And that's Lou Harriman and Joe Stiebrick wrote that. And Joe Stiebrick, that's I guess my last point here is there's a lot of great information on this on Building Science Corporation's website. So thank you for listening. Dig in, and I'll talk to you next time.
Thanks so much for listening, everyone.